Let's take a look at how a catalyst can affect the rate of a chemical reaction. A catalyst is something that will generally speed up a reaction. They could slow down a reaction, in which case we tend to call it a negative catalyst or an inhibitor because it's inhibiting the reaction, but most catalysts speed up a reaction. Okay, so they will change the rate of reaction. Usually they'll speed it up. Let's look at the reaction of zinc in hydrochloric acid. So the zinc is going to dissolve. Right? Put a metal into acid, you're going to get hydrogen gas, so we're going to have 2 of those, and we're going to make some zinc chloride, which will be in aqueous solution. Great, so since we're putting aqueous solution, let's put all our other symbols. There we go, so there's the reaction equation. Now, the zinc will dissolve. That will take a certain amount of time, but then we're going to have this same reaction occur in a separate test tube, but the second test tube will have a catalyst of copper 2 sulfate. Okay, so you've probably know copper 2 sulfate as the pretty blue stuff. Well, in this case, we're using it as a catalyst to catalyze, to speed up the rate of the reaction in which the zinc will dissolve. Right, so let's have a look. Here we have our 2 test tubes. Each one has the same mass of zinc. We weighed out 0.1 gram of zinc. It's important to remember to keep other variables constant, right? Only change one variable. So the variable we're changing in this case is the test tube on the right. This one has no catalyst. And the test tube on the left, since I finished this word, here we go. The test tube on the left has a catalyst. The catalyst being the copper 2 sulfate. Right, so we weighed out 0.1 gram of zinc, put it into a test tube. Into the left test tube we added just a few drops of copper 2 sulfate. Not much was actually needed. And what can we see? Well, hopefully it's clear that there are more bubbles in this test tube. Right, the reaction is more vigorous. The zinc is dissolving more quickly. Let's have another look here. Here's a different photo. Again, on the left we have the catalyst, so tick. On the right we have no catalyst. Let's give it a cross. And we can see, hopefully, well, I can see, hopefully you agree, that the test tube on the left, the reaction is really obviously occurring much more vigorously. We have a much more vigorous reaction. So the zinc is dissolving much more quickly and producing the hydrogen gas much more quickly. Remember from our equation that hydrogen gas is one of the products. That's what we're actually looking at. All those extra amount of bubbles, that's more hydrogen gas being produced because the reaction is going more quickly. There we go, we have a catalyst, and sure enough it sped up the reaction. So we can see that we have a visual of more product being formed quickly, but also the zinc actually took less time to dissolve. I don't have the numbers with me, so we're just going to have to look at the image. We can see, yep, the reaction is going faster. But yes, the zinc did dissolve more quickly when we had the copper 2 sulfate. So what is actually going on? Well, remember this graph here. We've got the energy of the particles up the side. We've got the time down on the bottom. Let's have reactants here and the energy of the products down here. So in this case, this is an exothermic reaction, right? Because the products have less energy than the reactants. Now, remember, we don't go straight like this. No, no, no. We form the activated complex first. We have to put in energy first before a reaction will proceed, and the graph goes up and then down. So at the top of the graph, that's where we have the activated complex. And this amount here of energy that had to be put into the system is what we call the energy of activation, or the activation energy. Now this applies equally to an endothermic reaction. We have energy outside, time down the bottom. Now in the endothermic reaction, the reactants have less energy than the products, okay, because the energy was absorbed by the system, right, as the reaction proceeded. But the graph goes up and then down to the products, right, with the activated complex at the top. And in this case, the activation energy, the energy of activation, is all of this. Okay, that's the activation energy. So this is essentially how reactions proceed. You have to input a certain amount of energy to overcome the activation energy, right, to reach that activated complex, which will then being an unstable, well, not a true molecule, but being an unstable chemical species, an unstable high energy species, it will then go and form the product. But we have to put in a certain amount of energy first. Well, what does a catalyst do? It lowers the amount of energy you need to put in. So let's draw a similar graph to what we just had. Let's have reactants up here, products down here. So again, we're talking an exothermic reaction. Now, an uncatalyzed pathway might be something like this. But a catalyzed pathway, in fact, let's label uncatalyzed. So that's the general pathway that the reaction would normally take. You would have to put in this much energy before the reaction would proceed. But now if we add a catalyzed pathway, it might look something like this. Okay, so red is catalyzed. We have a catalyst. In this case, what we can see is that the activation energy is less. Right? So with the catalyzed pathway, we have a smaller activation energy. What we have done is actually decreased the energy of activation that we need to input to the system. So if we don't need to have as much energy, to overcome the hump, that means that there will be more chance of a successful collision when the reactant molecules collide. Of course, the collision theory tells us that the reactant molecules must collide first, but they have to collide with sufficient energy. That sufficient energy is, enough energy to get over the hump, right, of the graph, to reach that activated complex. So by using a catalyst, by lowering the energy of activation, we're increasing the chances of a successful collision. Right? When the reactant molecules collide, there's more chance that they will have sufficient energy to form the activated complex, and then after that the product. Right? So that's how catalysts generally work. They lower the activation energy required for the reaction to proceed. Remember, the higher the bump, the harder it is for the reaction to proceed, so the slower the reaction will be. By lowering that bump, the easier it is for the reactant molecules to have a successful collision, or the more chance that the molecules will have a successful collision, because they don't need to collide as energetically. So there we go, that's catalysts and speeding up a chemical reaction by using them. Now, before we wrap up, we'll just look at one other quick example of a catalyzed reaction. This is a good one to look at. It's quite fun. So here we go. We have hydrogen peroxide, that's H2O2. This is a decomposition reaction. It will decompose to form water and oxygen. Now, you can't really tell when it's done because it looks like water at the start and we're making water. So, can't really see it there. You could look at the oxygen produced, except you can't actually see oxygen. What you can do, on the other hand, is put detergent in the measuring cylinder with the hydrogen peroxide, and then when the oxygen is formed, it makes bubbles. So there we go. We'll see the bubbles forming. Now, this is quite a slow reaction, but we use a catalyst of, in this case, we're using potassium iodide. You can use different catalysts, but this is what I use for this reaction. This is generally referred to as the elephant's toothpaste in the first example. And then in the second example, I actually didn't use detergent, but we can still see lots of bubbles of oxygen formed. And actually, by putting a thermometer in at the end, we can see that it got quite hot. It's quite an exothermic reaction. So in the second example, no detergent, and I had actually dissolved the catalyst in water. So we've got the two solutions being mixed in the second version. But let's take a look. "66 degrees. Okay.
don't forget to hit the like button. Yeah. And subscribe too. It's up here. And here's another video.